In this example, we're going to be seeing if a given matrix is linearly dependent or linearly independent. And so here's my matrix. Let A be the matrix given by 1, 2, 3, 4, 5, 6, 7, 8, 9. I know, I'm so creative, right? So, given this matrix, we want to see if it's linearly dependent or linearly independent. What does that mean? Well, it means that if I have the matrix equation, A times the x vector equals the 0 vector, if there's any solution other than just setting all my x's to 0, then it's going to be linearly dependent. Otherwise, if the only solution is what we call the trivial solution, this is just all zeros right here, then it's going to be linearly independent. So how am I going to go about figuring this out? Well, considering that we're talking about a matrix, I'm simply going to write the augmented matrix that corresponds to this equation. So I'll switch colors. So this is going to be the same matrix, and I'm going to write them this way since now we're thinking in terms of a system of equations. And so I'm going to have the equation 1x1, 4x2, 7x3 equals 0. Never forget what these numbers represent. These are the different variables in an equation. And the right-hand side, if you have an augmented matrix, is what it all equals. I'm going to have the second equation, 2x1, 5x2, 8x3 equals 0. And finally, 3x1, 6x2, 9x3 equals 0. Okay, cool. Now, first things first, we're going to be doing a lot of row operations to this. And so because rewriting this matrix over and over and over takes up a lot of space, I'm going to be doing probably 2 steps at once, but I am going to write right here what those steps are. And I'm going to say them out loud as well, so just stay with me. So first things first, I notice that my bottom row here, 3, 6, 9, can be divided by 3. So I'm just going to go ahead and do that. Divide by 3. And now think, hold it in your mind that if you do that, you're going to get 1, 2, 3. That's what all of these are divided by 3. What's nice about doing these types of problems is that since all of these are 0, you don't have to worry too much about this column over here. So I have 1, 2, 3. And what I need to try to do is to eliminate as many variables as possible. So what I'm going to do to get rid of the second row is I'm going to subtract 2 times row 1. Remember, what you do is you try to get rid of all the numbers other than the top left one here in this column. And then once we've done that, we're going to try to get rid of all the numbers below this point and then get a 1 down here. If we can, we're going to see what happens. So that's enough operations for once. I'm going to just go ahead and write this out here. My top row does not change. It's just 1, 4, 7, 0. My middle row here, well, I subtracted 2 times the top row. So I'm going to do 2 minus 2 times 1 is 2, so that's going to be 0. 5 minus 2 times 4 is 8, so 5 minus 8 is negative 3. 8 minus 2 times 7 would be 14, and 8 minus 14 is negative 6. And notice, 0 minus 2 times 0, it's still 0. So that's nice. All right, now this one I'll just rewrite. 1, 2, 3, and 0. Okay, cool. All right, so now notice down here that I can simplify this if I just subtract row 1. 1 minus 1 will be 0. So minus row 1. And I also notice that I've got negative 3, negative 6 here. So I'm going to go ahead and divide this guy by negative 3. I'll rewrite the matrix. 1, 4, 7, 0. Top row still doesn't change. This right here, 0 divided by negative 3 is 0. Negative 3 by negative 3 is 1. Negative 6 divided by negative 3 is 2. And that all equals 0. And if I subtract row 1 from this third row here, 1 minus 1 is 0. 2 minus 4 is negative 2. And 3 minus 7 is negative 4. And 0. Okay, I'm going to rewrite this matrix here. Here, I'm going to do the same thing I was doing right here, where I notice that they're both divisible by negative 3. These are both divisible by negative 2, so I'll go ahead and divide that. Can you see what's about to happen here? 1, 4, 7, 0. 0, 1, 2, 0. And, if I divide this by -2, that's a 1. -4 by -2, that's a 2. And then I got a 0 here. So we are going to take one more step, but let me pause and talk about this. Notice this row and this row are exactly the same. What's that mean? Well, it means I was able to get the same equation in more than one spot. So that seems to tell me that in my original matrix, it's possible to write one of these vectors as a multiple of the other. But let's go ahead and do like 1 or 2 more steps just to show that that really does happen. So all I'm going to do is subtract row 2 from row 3. So I'm going to have 1, 4, 7, 0, 0, 1, 2, 0. And if I subtract row 2 from row 3, I just get a row of zeros. And so remember what these columns represent. This is my x1 variable, my x2 variable, my x3 variable, and this over here is what they all equal, which in this case is the 0 vector. So notice what we have. Multiply x1 by something, add 4 times x2, add 7 times x3, and then we have 1x2 plus 2x3. Notice that x3 here, there's not really going to be a way for me to determine what he is uniquely, because I'll be able to solve this for x1 and have x2 and x3 over here. Likewise, I'll be able to solve for x2, but I'm going to have an x3 involved in everything. Let me go ahead and take one more step so you can see very clearly what I'm talking about. Let's see. I'm going to go ahead and subtract 4 times row 2 here. So 1 minus 0 is 1. 4 minus 4 times 1 is 0. 7 minus 2 times 4 would be 7 minus 8, which is -1. 0. 0, 1, 2, 0, 0, 0, 0, 0. And now I'm just going to translate what this represents into these terms. So this right here gives me x1 minus x3 equals 0. And this gives me x2 plus 2x3 equals 0. And if I solve these right here, I get x1 equals x3, just adding it to both sides, and x2 equals -2 x3. And we're not told what x3 is. When that happens, we would say that x3 is free. It means you can choose any number at all that you want for x3, and then using that value, you'll be told what x1 and x2 are by these equations. So what does that mean? Well, I could pick x3 to be 7. And so if I do that, x1 would be 7, and x2 would be -2 times 7, which is -14. What matters is that's not all zeros. So there's a solution to this, a way to make all of this true that doesn't involve setting all my x's to 0. And when that happens, if this has a non-trivial solution, which really just means bad grammar here, but non-all 0, then this is linearly dependent. I can write one of these vectors as a multiple of the other and get all zeros. And that is this example.